Hello, my friends, and welcome back here in GSC 109, or General Physical Science, and its accompanying lab. So this week, we are exploring the universe one star at a time. Today, we're going to be delving into something every astronomy student needs to know about, and that is the Hertzsprung-Russell diagram, a wonderful data set that helps us conduct a survey or a census of the stars above. We typically call this an HR diagram. And this is, again, it's like a cheat sheet for us to be able to learn more about stars and the astronomical phenomena that they provide us for use of study. It tells us about the properties of the star and even the position of the life cycle. So grab your notebooks, grab your database for the week, and let's work together on being able to build one of these HR diagrams, a essential tool for all astronomers to learn more about the night sky. To really bring the phenomena to life, first, let's take a look at the historical astronomical phenomena, the Great Eruption of Eta Carinae, that occurred in the mid 1800s. This star was about 7,500 light years away from Earth, and it suddenly became one of the brightest objects in the night sky. Eta Carinae is a massive, unstable star, what we commonly call a supergiant. Its incredible eruption was dramatic, caused a dramatic jump in its brightness that changed its own position within that HR diagram from a high luminosity star to an even brighter point, revealing just how dynamic the life cycle of stars truly are that illuminate our night sky. This eruption was a critical reminder of how stars evolve and change and grow old, just like we do. And we can track this progress using that HR diagram. This phenomena will allow us to ask the big questions and gather robust information to be able to learn more about the phenomena, but make our hypotheses or our scientific claims much more concrete because the data that goes into the HR diagram helps us learn about how data drives scientific knowledge. So let's get into the basics of a HR diagram. The HR diagram is a graph. It's a scatter plot that maps stars based on two main properties, luminosity and brightness. On the y-axis, their surface temperature is generally found, whereas on the x-axis, it's brightness. But here's a twist. The temperature scale on the HR diagram can sometimes be flipped because it's all about scientific communication with hotter stars on the left and cooler stars on the right. This reverse layout may seem a little strange to you, but how we use those axes in relation to the data points can be very important because we can use it to organize spectral types of stars and use the spectral class as a form of communication that allows us to bring in different parts of our data set that we're going to be generating this week. Let's take a look at the HR diagram and go over a few key points and explore the different regions. Most stars, including our garden variety sun, falls along an area we call the main sequence. Stars on the main sequence are the prime of their lives. They fuse hydrogen and helium together and cause chain reactions. Think of a nuclear power plant. And they can also come in a variety of different types, from hot blue to red ones, but they're still typically found within that sequence. Then we also have the giants and the supergiants. These are going to be your more massive stars that have moved off of the main sequence and have aged very well and expanded, much like a fine wine over time. Then down at the bottom, we will have the white dwarfs. These will have used up their fuel and are become super dense, maybe indicating a end of life process. One of the most exciting things about the HR diagram is, again, how it shows stellar evolution. And that's something we're going to be learning about more as you conduct your capstone research. A star's position on this chart will never be static. It changes as that star ages over time. For an example, our sun will eventually move off of the main sequence as it burns through its core hydrogen and expands into its red giant era or phase. And will finally shed its outer layers as it expands and then eventually becomes a white dwarf. And the journey across the HR diagram is how astronomers map out the life cycle of stars as we classify them. This provides us with insights on truly how old our universe can be. Now, why is the HR diagram so important in astronomy research? Well, for starters, again, it helps astronomers estimate the ages of star clusters that we cannot travel to in the current state of technology. It helps us also analyze where stars are falling within the main sequence, but it also allows scientists and astronomers to make educated guesses or hypotheses to guess about what we observe in the night sky. We can learn a variety of different things, such as the mass of stars, in even its distance, and even the chemical composition of what is occurring on those stars as those reactions are playing out. This unlocks valuable data about a star and its properties. Now, we can take a closer look at some of the different types of stars. There's also what we call red dwarfs, which are small, cool stars, and they sit in the lower right of the main sequence. These stars will burn slowly, giving them incredibly long lifespans, in contrast to the massive blue giants, which are hotter and brighter. And these are typically going to be found in your upper left. These stars live fast and die young, and often end in spectacular supernovas, like what Eta Carinae may have been, because there's a significant distance in time between our observation and what is occurring. Each type of star type, such as giants, supergiants, and dwarfs, all again have unique properties that reflect temperature and luminosity. And that's why we want to go out there in our capstone research this week to chase down these facts and provide evidence to support our scientific claims as we learn more about stars. All right, so this is where we start to begin our research, and so we need to ask that why should every astronomy student get comfortable with an HR diagram? Well, answer's simple. It's because the chart acts much like a roadmap for studying the stars. Whether you're observing a new star cluster using resources like our Stellarium program, or mapping out stellar evolution, or just getting to know the stars in the galaxy, the HR diagram is going to be our go-to guide. And we are going to be making that guide in this week's lab, but then also as part of your capstone research to be able to compare or contrast constellations and the asterisms that belong to those constellations, and how do they compare against more commonly studied stars and constellations. It will allow you to reveal patterns and help you understand better the stellar properties and evolutions on a much deeper level. Essentially, find out our place in the sea of stars, because our sun is just one of many, and it allows us to build a foundational tool in the world of astronomy. So, thank you again for joining me this week as we learn more about stars and spectra and the HR diagram, and use it as a way to delve deep into astronomical phenomena. Remember, every dot on that chart represents a real star that you can study. and it has its own story within the cosmos. If you want to learn more about stellar evolution, try plot using your own generated HR diagram based upon the data you're building on your capstone. The methodology can be applied to any star. Don't forget to check out the awesome resources I have provided for you this week, such as the Hippocarius database. And as always, if you have any questions or need help working with the data, I am here to support you in your learning journey, either through an in-person office visit, an email, or video chat. And let's continue our journey through the universe and keep looking up.